From DataStax, this is the Distributed Data Show podcast.
And hello, everybody. Welcome on this Tuesday to another episode of Graph Data and Code with Denise and David. I am David Jones-Gilardi, joined yet again by now the more remote than usual, Denise Gosnell.
Yes,
Denise,
thank you.
Where are you, Denise?
Well, coming to you live from Abigail and Evelyn's bedroom. I am with family, and all of the whole house here is super excited to be a part of the live show this week.
So you've stolen their bedroom for our
I have. My nieces have generously donated their bedroom for our live show.
Well, it's very nice of them. So thank you for letting your aunt steal your room for the live show.
Yeah, they're super excited about it. I have quite the audience today.
Are they all behind you right now, like over there behind? Well,
yeah,
not that way,
they're all
that way.
generally abound and poking their heads in and whatnot. It's quite fun.
That's funny. So today, right, we're gonna continue on chapter 6, right? Give maybe a little recap about what we did last time and what we're gonna do today.
Yep, that sounds great.
Wonderful.
Yeah, let's do that. So I think we want to start off. Hey, this is Evelyn. Hi, Evelyn. We want to start off with doing a review of last week. Thank you so much for coming by to say hi, Evelyn. And we're going to start off with watching the video to review last week's problem. Is that correct?
Yes. Yeah, we're going to take a look at the video. But before we do that, for those of you who are listening with us today, we have something a little special. So if you've been following some of the other things that have been coming out of DataStax, you may have noticed our Accelerate online conference. And the last episode dropped, right? The very, very, very last one. And in my opinion, it was epic, right? And I did not know this was even happening. So I was like just as surprised as everybody else. And what we ended up doing was creating a bunch of, how do I put this? Like different music tracks that were database inspired. I've never heard database music before.
I mean, maybe we need to make a new genre of music.
I think so, right? And so anyway, I'm really excited about these. So I want Alex, if you would, Alex is going to go ahead and just play just a little bit of one of the EDM ones. There's multiple flavors. There's folk one, there's EDM, and then the other one was pop. But yeah, if you could just play a little bit of that totally database themed music.
Yeah, I think we had a little too much fun with these. They were one of my favorite projects we've done here today.
So I see it's playing. I don't know if we hear it.
I can't hear it from my end.
It could be just because we don't hear it. There it goes. Give you just another moment of that, just to give you a feel of this like awesome music. And where you can get that, I'm actually going to drop the link in both the YouTube chat and this music. You can go take a look at SoundCloud. It'll eventually show up on Spotify as well. But I've never actually heard music one that was database inspired. But you got to listen to the lyrics. It's a key thing. There's 3 songs.
They really are.
The lyrics are awesome, and anybody who's done anything with databases, you are going to be just cracking up as far as I'm concerned. So thank you, Alex, for playing that. I appreciate that. Wanted to get that in there.
Yeah, I'm trying to remember. It took me a few times. So I was involved in the pop one, and it took me a few listens to really get in there and understand the lyrics and all of the puns. And I mean, we're big fans of puns on this show. They were probably some of the most creative tracks. I think one of my favorite parts though was the timeline evolution from, relational to NoSQL to the future of the cloud. I think that was my favorite way that they kind of brought all 3 of the songs together. I'm glad that we got to share that with our audience. So
yeah, totally. And by the way, hello, Kamal, Vikrant, and Ashish. Yes, you can hear it. Sounds good. Awesome. Yeah. So anyway, there's the link. Go check it out. It's actually really good music. I've been listening to them like in my regular tracks now.
Oh, okay. So you're gonna out yourself? No.
yeah, honestly, yeah, totally. All right. Yeah. So I guess folks are here to listen or to watch us go through graph stuff, maybe we should
let's do that. Let's do that.
By the way, since you were involved, I have to say nice job on that one. That one was that whole episode was epic.
It was epic, and I don't think I can. I don't think I'm going to be able to not hear the index song in my head. So it's always there now.
Oh yeah, you know what you can do with the index song? Just play it to Rebecca. Was it Rebecca Black's Friday?
Yeah.
You're welcome. Everyone who's listening, you're welcome.
Oh gosh, I had not thought about that. Thanks.
All right, so with that, you were telling me we should probably bring up the video here to go ahead and start off with our recap of last week. Is that correct?
Yep. Yeah, I think that'd be great. Yeah, so go ahead and press play on that.
Get it?
And so where we're going to start, we are in the second main example where we're looking at time series data in a graph. And we're specifically working with the power grid network and just within the Seattle area. So we've got two types of vertices, sensors and towers. These sensors are collecting voltage levels and passing that reading to another nearby sensor or tower that's available. The reason that graph databases are so powerful for this example is that they're really great for understanding real-time or near real-time failure scenarios. Say if a tower goes down, like you saw in the video, and we can then detect which nearby sensors are at risk for no longer being able to communicate with the network. Once those sensors can find new paths throughout their communication trees, they're able to reconnect to the network and rejoin. And once the tower comes back online, they can reestablish their original connection to the tower. The way those connections work are hardware details with the sensors. What we're focusing on are how the payload exchanges from one sensor to another sensor or a sensor to a tower can form really interesting trees throughout the graph, throughout this dynamic graph. And we can use these structures to figure out which sensors are at risk in different failure scenarios. So that was the video. Thanks for teeing that up. Yeah, and last week we did half of the queries, I believe. So when you're working with these, when you're working with trees in graph databases, you can go from roots to leaves or from leaves to roots. And I mean, mathematicians and graph theorists just love to use all these different terms. A root really is like what we're thinking. It's the top of a tree or the top of your data. And then a leaf is the very, very end when you're walking down this nested structure just to one piece of data. And we did the easy way last time. We walked from leaves all the way up to roots because that's one half of the query that we need to do.
From our sensors to our towers?
Exactly, from our sensors to our towers.
Okay.
Yeah. So let's, David, do you want to walk through? So last time I was doing some of the teaching of the queries that we were doing from sensors up to towers.
Okay.
And so can you refresh maybe and just start off with some of the queries where we were walking from a sensor to one neighborhood to two neighborhoods and just kind of catch us up briefly on where we were.
Yeah, that's right. So if we take a look here at line 1, and hopefully, by the way, I've blown this up usually to the size that we do it in these. But if it's too small for anybody, please let us know in the chat. We will watch and I will blow it up a little bit more, but I do try to make sure we're zoomed in right off the bat there. But in this first line, we're essentially filtering for a specific sensor, right? Sensor 1002688. And then we're going to go next, right? That's actually right there. Next is going to return that particular vertex. And we're setting that to our sensor variable here that we then get to reuse later on, right?
Exactly.
Now, Denise, you've kind of explained why that's useful. I mean, I could see why in certain cases, if I had, say, more complex examples where maybe I had a bunch of different, say, references or objects I would want to store it in a variable like this to use it later. Are there particular use cases that you see for doing it that way?
And can you just break that down? I was trying to follow you through that. I knew you were going to get to your question. I was like, I'm not quite.
Eventually, he'll get to his question. It's going to happen eventually.
There are going to be other use cases, but can you just repeat that?
Yeah, well, like in this case, I think it's a very simplistic example where I only have this single variable sensor that I'm using later on for reference, right? Mm-hmm. What would keep me from just plugging this right in to my traversal here as compared to using a variable reference and passing it? Was it just an example or is there, you see what I'm saying?
I do see what you're saying. And, this was just an example of two different ways to do the fastest possible lookup of a vertex in a graph that's represented in Cassandra. So in an actual production application, if you already know the strong ID that you are looking up, if you know your full partition key or full primary key in Cassandra, you would just go ahead and use what you see on line one and line one in your traversal that starts on what, line 3?
Yes.
Yeah.
Okay,
So this is just
really
for example purposes.
Multiple ways to do the same thing. There's, again, to me, I've used variables. I was kind of just throwing that out there, and I didn't really warn you that I was going to ask that question. I've used
that's
this.
what we're here for, right?
Yeah, right. Yeah, I've definitely used that in cases where if I have a bunch of different lookups I need to do in like a whole set of traversals, I may do a bunch of variable definition like right up front and then use them later or something. I just didn't know if there was some benefit or specific, reason in this case, but it sounds like it's just an example. Here you go.
Yeah, and actually, David, as you were talking about that, you just reminded me why we kind of developed this as a pattern to begin with, is that you might have this useful vertex, and there could be a few different calls you want to run, in parallel or asynchronously, so that you're looking up many different items about that individual vertex. So then you would store it as a variable and then kick off your many different graph traversals at the same time, starting from that single place. And that could be one way. You could be passing that object into different parts of your code. Just depends on the type of structure and framework that you're using.
Okay, great. So now going back to what you actually asked me, right? Because I just totally went off to the side there.
That's fine.
So then looking at a traversal, again, we're using dev, right? Dev dot, as I understand it, unlike doing g.v, is a developer traversal that does very quickly and easily allows you to just essentially run your traversals without some of the constraints like indexes and such that you may need when you're running in production mode. So as I understand it, this is not something you'd want to do in production. This is something as you're building up your traversals, you can use to very quickly switch into that mode. So yeah, there's the dev.v. And then we're going to go out. So we're at our sensor, right? So if I look at our schema over here, we're going to go out the send edge to find, well, a tower or potentially another sensor, right? It really depends on what's out there, but we're just doing a single out, right? So we're going to go out. Matter of fact, if I have that, we're going to go out once, but out each one of these, correct? So it could be a tower or a sensor? Because we're walking all send edges?
It could be.
Okay, so it could be a tower or a sensor.
Yes, yep, and that's exactly.
Okay. I didn't know if you were going to say more there on that one.
No, and I also was troubleshooting some audio that I was breaking up over here. But yes.
Oh, okay. It got quiet for a second, and I'm not watching your face. So.
Yeah, this is going to be an interesting show today with the internet bandwidth where I'm at.
Okay, so then once we then walk out, we're going to walk some gremlins out over those send edges, and then use the project step, and both project to label and name, and then using the by operators. In this particular case, the first one we're going to get label. I'm assuming, do these have, we want to get the value for the first key there, and then we'll display that. And with coalesce is essentially just like an if then, right?
Exactly.
So if we
I
find
love that.
Tower
That
name,
was perfect. It's like an if then.
So if we find tower name, great. But if we don't, then we'll go ahead and essentially else on the sensor name.
Exactly. That's it.
Run this. We should see something like that, right?
Perfect. Yeah. And so what David is walking through here is with the larger problem we're trying to solve. We're trying to figure out if an individual tower in this network goes down, we're trying to figure out which sensors had connected to that tower at all. And then for each of those individual sensors, what towers did they connect to? Because if there's a sensor that only connected to the tower that went down, that's the sensor that's going to be at risk. And that's the information we would share with the power companies so that they can send their fleet of vehicles to a smaller subset to resolve their network issues. So at this point, we're walking from a sensor all the way up to determine how many different unique towers it connected with. And that's what we did last time. And David's just kind of showing you the pattern that we used for those queries. And this first neighborhood, we continued last time. I think the next queries that David would walk through, or David that you could walk through, just kind of take this exact same pattern and walk out 2 and 3 neighborhoods. Correct.
Right, because right now we're only walking out the one neighborhood. Right. Now,
Yep.
and just be clear, so what we're seeing in the results here is that at least in the first neighborhood for this particular sensor, we see that it has both a tower, the Georgetown Tower, and a connection to another sensor over here.
Yep. And that's the really cool part about this example. So the details of what a sensor communicates to, I mean, that's implemented as a part of the hardware on how these chips and sensors are designed. But what happens is that these sensors, on an interval, are looking throughout their network to communicate with anything nearby that's available.
Right.
And so in this example, it's showing you that there was a communication that went directly to a tower. And then there was another point in time where it connected to a sensor that was nearby. And that dynamic connection, or that dynamic edge, is how we're getting these different paths that are forming throughout the network.
Okay. And again, this was just first neighborhood. So we're just going directly from that sensor to whatever it's connected to. And that's it right there. We stop.
Yep.
Okay.
Yep. And so, I think the queries we built on last time, we don't need to redo them, but we just essentially added 2 layers. We went out to the second neighborhood, and the next query went out to the third neighborhood. Yep, that you can see there that you're highlighting.
Right. You see again. So in this particular case, just to make sure that we're all on the same page, it's the same exact traversal, right? We're doing the same stuff. The difference is that we have multiple outs. So we essentially keep going to each subsequent neighborhood. And as you notice in the results in each one of these, right, we're getting slightly, our results are kind of expanding a little bit, it seems. Mm-hmm. And is that, if I have it right, let's say from the first, you're over here, from the first initial sensor, that let's say we walk to a tower, but then we can say outside again, well, we might walk to another sensor or something, and then we walk from there, and so on and so forth, as much as we keep adding these out sends.
Yes, exactly.
Okay. And
the reason that we're getting that we have more results as we walk further is because of branching factor.
Right.
And that's going to come into play when we work in reverse. So that's just kind of the teaser for what's coming. The graph term that we're going to be talking about today is called branching factor.
Oh, cool. And I'm also going to make an assumption that, this is a very manual way to want to go to multiple neighborhoods, that there's probably a way that we can just loop through those.
Absolutely.
A straight person with myself right now.
and that's exactly where we, so in the last 5 minutes of the show, we kind of showed that last time, and it was pretty quick. So what we don't want to do is run this next query, because this query has no stopping condition on it. Right. The problem with this query that you're looking at here is that we decided, to your point, that it's very manual, just to say we're going to walk out X number of neighborhoods. Right. Instead, you want to walk from a sensor and keep walking out these communication trees until you find any connection to a tower.
That's right.
Right. But we want to have a stopping condition, and we don't want things to go on infinitely, like a sensor that goes to another sensor and comes back to the start, because that would never terminate. And so that's why we're not running this query, but instead we added in simple path in the following one.
That's right. And correct me if I'm wrong, I believe in last week, one of the reasons why, the way you guys built these out to do it in this manual way first before you used a repeat, is if you're building your first traversal and you're figuring out how to do this pathing, that it's probably good to start with the manual option first. Yes. Start with the manual traversing over your edges and figure out the actual logic of your traversal before you start adding in repeat and such, and making it a little bit more complex that way.
Exactly. And I guess it's how I approach every new query I'm trying to write with Gremlin. I always start with bringing together pieces that I understand and slowly building one step onto another step, and also bringing in common patterns of how I like to shape my payloads. Using project by is my go-to for shaping my data payload, in addition to coalesce for if-then, like you were mentioning, for different types of data that you might need to have in your payload. Yes, so okay. Absolutely.
All right, so the lesson with this particular traversal, though, the one that we have that I'm showing on the page, is there is no end in sight. This one will just infinitely keep repeating. You probably don't want to run it. Now, if you do, by the way, if I do run this, it'll actually give me the ability in Studio to kill that. Mm-hmm. You can do that. But if you ran this in your code is just going to sit there. It's never going to return.
Right. And it's never going to return because you're going to get infinite loops of running or walking from one sensor to another sensor and back. It's just going to keep going. And that's the beauty. We have one step for that in Gremlin. It's called simple path. If you have a traverser that starts, if you have a traverser that's walking a path and it finds its way back to where it started, it's going to go ahead and terminate. Just that individual traverser, not the whole traversal, just that individual walk that you're exploring in your graph is going to terminate.
So in the case here, I think this is one of the ones you said is actually going to be pretty long running, so I can always kill it if we need to. So here we've got the same traversal as before, but now within our repeat, we also has this simple path, right? So by using simple paths, is it true that it will in fact terminate once it is finished, essentially, its walk? It's not just going to keep going circular through the same sensor and coming back out or anything like that, is it? Okay.
Yep, and the thing you're doing there with this is my favorite part about graph theory and graph traversals is that it's very intuitive. Like this, what you're doing with your arm is a cycle, and it makes sense to think of it like this, like you're in a circle. And any type of individual walk in your graph that finds its way into one of these or into a cycle, that's what simple path does. It removes that from your result set. And every other traverser that's walking here is starting from a sensor, and it's walking through any combination of edges until it reaches a tower. And that stopping condition, I believe, is what we have on line 5, until starting at this sensor, repeating, walking out until you get to a tower, and removing any type of cycles. That is exactly what this traversal is doing.
So it's interesting that, this one did finally complete, and we have like 1,000 results here from this one sensor.
Yeah.
And if I'm correct, this data set is actually from a real sensor network, right? This isn't like a contrived data set. Is that true?
So I had the real honor to get to work with a real company for this, and I couldn't lift their real data, but we have real towers, we have real sensors. The edges look very similar to the type of network that they have, but they are, for the purposes here, they're synthetic.
So at least for, the case of like applying this to a real world scenario, do you find that the amount of results here, we've got like 1,000 hits that is actually kind of, comparable to what they actually see? Because to me, this feels like this is starting to like contextually give me an idea of how complex this network might really be.
Yeah. And what you're seeing and experiencing is what we call branching factor.
Okay.
So can we throw back to like Nintendo 64?
Let's do it. Yeah, let's.
Maybe. Is that something that did you ever like play Mario Kart on Nintendo 64?
Oh, totally. Yeah, of course.
Do you remember that one level with I think it's called Yoshi's Valley? Do you remember that level? Like where you start and then you have all of these different paths to take to get to the end of that level in Mario Kart. That's what branching factor is. It's seeing all of these different paths and realizing that you have, tens of combinations, hundreds of combinations possibly, of how you're going to get from your start to the end. And at every single different intersection point, there's 2 or 3 new paths that you can take. That's what branching factor is. Branching factor.
Like a fractal at all?
Say what?
Is it kind of like a fractal at all?
It is exactly like a fractal. So a fractal has a fixed branching factor. And so they're going to create these really beautiful mathematical patterns.
Yeah.
Real world graphs have more like a scale-free distribution in their branching factor, where sometimes you'll hit a vertex that's extremely high degree, but most often you're going to hit a vertex that's very low degree, and that's what scale-free means. So most of them are going to say only have 2 or 3 options. I think on average, the graph structure we're working with here has up to 7 different branches on every individual vertex. Okay. And I mean, branching factor can really affect the performance of your traversals because of the exponential growth of the number of elements that you're processing.
Right.
So you always have to make sure when you're walking through paths or trees that you're limiting the number of choices that you make to ensure that you're minimizing the total paths that you're exploring. Just like if you were, playing Mario Kart back in the day on Nintendo 64 and you're on Yoshi's Valley, you're going to try and find the shortest path through all of those different turns when you're playing that game, instead of picking the longest one or exploring multiple. So I don't know about you,
That's
but
right.
Yeah, go ahead, David.
Please. Yeah, go on.
Yeah, I don't know about you, but whenever I played Mario Kart on the Nintendo 64 and I was on that level, I made sure to find like the fastest path and always go through it. So that's one way to think about data's branching factor in video games, because I tend to like to map graph data to video game examples.
I'm okay with that, honestly. I like that comparison myself. And I feel like this makes a lot of sense, especially if you're talking an OLTP graph, right? Where you need kind of like online response times. That branching factor seems like it's really relevant there, and you need to understand what's going on with your branching factor, because I don't think I would probably want to execute a traversal quite like this without any like limits there in my OLTP setup, right? I may do this for more of analytics, or if I really want to traverse everything, but it sounds like we're going to need to limit things a little bit as we move forward.
Exactly. And so this is kind of where we left off last week, and we were able to successfully go from a sensor up to any tower. And so next, I think we're ready to move into walking in the reverse direction.
All right. Oh, okay. Wait. Oh, so we have one more here because we are.
Oh, we do. Sorry.
Yeah. Let's see what we did. Oh, I think you know what we're doing. We're getting, I believe, yes. Here's the same traversal as before, where we go to the simple path, but now we're pulling out a different set of data here.
We are.
And the tower name or sensor name.
Yes. I see. So what we're doing on this example is we brought in. So when we saw the results of the last one, David, we just saw the end tower, correct?
Yes, that's right. We didn't shape the results there.
Right. Yeah. And it's useful to know that from sensor 1002688 that we ended at the Rainier Valley Tower or the White Center Tower. But what we really want to know is we want to understand the path it took on the way. So for every individual traverser that successfully walks from our starting sensor all the way to a tower, we want to know a little bit more. We don't want to know just the tower it reached. We want to know the path it took on the way. So that's all we've added at the end of this traversal. Once we get to the end where we were repeating out until we reach the tower and we get the simple path, which is removing our cycles. For every traverser that successfully reaches that point, we're going to label that on line 9 as a tower because that's where we are. The traverser has walked from a sensor to a tower. At that point, what we want to know is we want to know the full path all the way from the beginning at 1002688 to the tower at the end. And that's the step that we're adding there on line 10. It's the path step. Nice. So it's pretty simple. We just want to know the path that you took through the data from the start to the end. And then we use the coalesce trick again to shape the results of your path. And so on the way, there's only 2 types of vertices. You're going to have a sensor or you're going to have a tower. So that's what we do with the bimodulator again on line 11 and 12. For each vertex, if it's a tower, tell me the tower name. Otherwise, tell me the sensor name. Nice. And that's the result payload that you're looking at now. You're looking at the sensor IDs that reached or that went from the starting sensor 1002688 to various sensors along the way until it reached a tower.
Interesting. So you're seeing the paths of every one of these from this sensor.
Exactly. And so I bet you if you scroll down, you probably could find a very long path.
There's a good one. Maybe there's one that's even bigger.
Yeah, I'm sure there is. It'd be at the very back, but there's, I mean, as you saw before. Right.
As it's going, you're going to be getting further and further and further.
Exactly. So as you find a successful, as you reach a successful tower, it's formatting the path. So the shorter ones are more likely to reach the end first.
Oh, very cool.
So yeah, so on that one there, from where I am, because of the setup, it's hard for me to read them. But if you kind of think and read through those IDs, you know that you started on 102.688, and then the next ID is where it sent its first message. The next ID is where it sent the second message, then the third, then the fourth, until it reached the tower at the very bottom.
I see. By the way, we have a question here from Chandran over in LinkedIn.
Oh,
says,
okay.
The traversal is an implementation of any standard algorithms like Dijkstra's shortest path?
These traversals are implementations of breadth first search or depth first search. So when we're doing these, we're just doing BFS and DFS. For Dijkstra's and shortest path, that's going to come in to play. Yeah, so for different shortest path examples, that's going to come into play in Chapter 8 when we're quantifying trust in Bitcoin exchanges. And you're trying to understand for who exchanged Bitcoin with who in the Bitcoin OTC network. You know, how do you quantify if you trust somebody by looking at the shortest paths between 2 wallets on Bitcoin? So shortest paths are coming, Chapter 8.
Cool. Okay. And so hopefully that answers your question there, Chandran. And let us know, and we'll watch the chat if you have a follow-up or anything else.
Yeah.
And then looking at this last traversal in this particular section going from leaves to roots, it looks like, again, it's the same traversal, right? But now we are assigning labels.
Yes.
To our path data here.
Yes. Yeah. So depending on which type of traversal you are running, and we don't need to rerun this one because it's the exact same thing. you can use labels to format your payload just a little bit differently. This is all coming down to what I like to talk about as, say, like the API contract, or the payload contract that exists between applications on your different microservices. Okay. That your API has to follow a specific structure or a specific payload, and depending on what you need that payload to be, using labels might help you format that payload a little differently, which is what we're doing here.
Okay. All right, cool. All right, so then now we're switching over, as you mentioned a moment ago, to go from root to leaves. We're going to start instead of the center and start at the tower.
Yes. Right. So just kind of zooming back out for a second, we were really deep in walking from a sensor all the way up to towers. And that's what we're saying from bottoms up or from leaves to roots. And now we need to flip it, and we need to go from top down or from roots to leaves. The reason we need to do this is because if you're thinking back to the bigger application, if a tower goes down, we need to understand which sensor is connected to that tower. So you'd walk from the tower all the way back to the sensors that connected to it. And then for each of those sensors, you'd walk out to their unique set of towers to figure out if they're going to be at risk of no longer being able to share their information with the network. So we're doing this in reverse. We went from sensors up, and now we're going to go from the towers down. And we did it this way because right when you walk from roots in any hierarchical application, when you start at the top and go down, you get hit by branching factor right away. That's when it starts really affecting you, because you're starting at the top and you're branching as soon as you start querying, instead of starting at the leaf and you probably only have one or two connections. So
I see that.
That's why we did it this way, just to kind of get the pattern down of how to think and how to work with this example, starting from the easier direction first.
Okay, got it. And we have a question over on YouTube from Mankata. Said, hello, David and Denise. Talking about the optimization. Yeah, hi. Talking about the optimization. Can you share the chapters on the optimization that Denise was talking about 2 sessions ago?
The chapters on optimization are somewhere lost in the bowels of my laptop. I'm still looking for them. So whenever you develop books with O'Reilly, this is probably one of my favorite experiences. So the answer to your question is, I have a request open with O'Reilly to get me access to a development branch from about a year ago, to get access to it. And we will keep working with O'Reilly to get access. The longer explanation is that there is a GitHub project that is behind this book. Once it moves into production, they go ahead and close it up and they ship it. And so I need to get access to that GitHub project again, and then pull # branch and try and re-render it. So we're working with O'Reilly right now to see if we can make that happen.
So Venkata's laughing, by the way.
Okay, great.
So I would say, Venkata, on that one, feel free to reach out if you haven't to either one of us on LinkedIn or whatever. It sounds like Denise is already working it to try to get those materials. But then once that happens, we can get those around to you.
Yeah. And just for the audience who's listening and wondering what that one is, it's been the most popular request. They're looking for some of the drafts. There's a ton of chapters that did not make it into this book. And the draft that we just previewed, and I was not expecting to be so popularly requested, was a quick overview of the algorithmic complexity of the most common graph algorithms. So I just kind of went through the O of n complexity in terms of number of vertices and number of edges for the most basic graph algorithms, and that is the chapter that needs to be discovered somewhere.
I think once you get all that material, you should re-release something called Denise's Brain, and then just have that all laid out in there.
Yeah. Thanks for, maybe we can try that.
All right. So going to traversals, should I run this one? Oh, I ran it, so there we go. All right, so we haven't really done this one yet. I know you've been walking me through these.
Oh, yes. Okay.
Let's see.
So this example here, this is the setup query, correct?
Yes.
Okay.
Yes. This is the subquery. Yes, it is.
Yeah. So for the setup query, what I was thinking for this query is I wanted to show you all how I think through problems. And when I started this problem, I realized that there was all these setup queries that I was writing in different notebooks so that I had good examples for the textbook. And after we looked at the first draft, we were like, it would be really nice if we just kind of showed people how we thought through and came up with the good examples. And so that's what this query is. We wanted to make sure we picked an interesting tower so that once we had a good tower, we were walking through meaningful examples for the full text. And instead of just telling you, hey, we picked the Georgetown Tower, I wanted to let you all see how I came up with that. And that's what this query is.
Okay.
So this query, honestly, if you're following along in the bigger application space we're writing, this query is not a part of the failure scenarios. This is just a setup query for more of like the how do I explore my data and understand what's there. So what this query is doing is it's determining of all of the towers in our graph, I want to know the total number of edges for each tower. And then I want to sort that tower list according to their total number of edges. So it's a very common thing to want to do in a graph database. This is called the degree distribution. And we've talked a little bit about how natural graphs follow a scale-free distribution where you have a few you have a few vertices that are very highly connected, but most of your vertices only have a few edges. And that's going to be a scale-free distribution. So depending on your graph that you have, this query is a fantastic analytical query to take either all of your vertices or maybe a certain label. We're doing in this example, just show me the tower label. And then I'm going to make a group. I'm going to group all of these towers. So we're making a map, essentially.
Okay.
We're going to call this map a degree distribution. So line 2 is saying, name this map degree distribution.
Okay.
Line 3 and 4 are the keys and the values of the map. The key of the map is going to be the tower's name. The values in the map are going to be the total number of send edges coming into the tower.
Oh, right. And the key thing with this in here is that since we're this time starting at the tower as compared to the sensor, then the edges are coming, the send edges, right? They're coming into the tower. So
exactly.
Those.
Exactly. Okay. And what you see there on line 4, David, is actually a really very interesting optimization on line 4. So it says by in e send.
Right.
You would get the same result if you did by in send, because you would still have all of the instance vertices that went into the tower. But there's a very, very big difference between in e and in when you're working with distributed adjacency lists in Cassandra.
Okay.
The difference is one of them looks up to another partition and the other stays in your existing partition.
I was wondering if just the fact that we are not fully walking to the end vertex that's attached to that edge, we're just counting the edges. I was actually wondering if that would be more efficient just because you don't have that extra step.
Exactly. You don't have the extra step. And when you're working when you're working with Cassandra, it's all about minimizing the number of times you look up different partitions. And so by doing in E, you're staying within the partition of your tower vertex, and you're just glancing at the number of edges it's pointing to instead of walking all the way to the vertices in another partition and then counting.
Yeah, that's a cool optimization. So something to keep in mind, right? So if I've got that right, to just kind of say it back, when you are, working out your traversals and you've kind of figured out, in this case, like we kind of know where we're headed, then if there are steps where, is it like a general rule that if you can count edges, do it as compared to going to the vertices? Is that like just kind of a rule?
I would say more often than not, that's whenever I'm working with companies and teams around the world, that's like one of my first recommendations. When just depending on where they are and what they're doing with their graph, it's like, do you have to go all the way to the next vertex or can you just use your edge?
Okay.
That's probably one of my most popular recommendations.
Cool.
Awesome. Yeah, so in line 5, what we're doing is we're introducing a barrier step. Now, what this barrier step is requiring, it's saying, Gremlin, all right, I need you to go do this for every single tower before we move on. So it's almost like asking the entire traversal to pause until everyone's ready to move forward. So at line 5, in my mind, because again, I think about Gremlin steps kind of like marble run, where you've got all these marbles flowing in tubes. I like
that. No, that's really good.
So we have all these gremlins or marbles going through all your graph, throughout your entire graph, and then we're bringing everything together back to one stream and asking it to hold and wait for everyone to catch up.
Wait for all the marbles to stop bumping around and stop walking through and get to their ends. That's cool. I've never had anyone explain a cap step like that before. I kind of wish that analogy would have been used when I first learned about cap.
Hey, I'm glad. I've always been hesitant to kind of let everyone else see how I see Gremlin because I'm, kind of concerned I'm just going to be that weird kid, but that's okay.
Oh, that's great.
Anyways, so once you have your entire map, so at line 5, once you move on after 5, you have your entire map. It's going to be called degree distribution. And what we want to do is we want to sort it. We want to sort this map So we're going to sort just inside this map according to the values. And we want to look from the most connected tower to the least connected tower. So we're sorting it by descending order on the values. And that's why we see that the top connected tower is Georgetown.
So is that also, since we just want to sort within this map, why we are ordering by scope local?
Exactly, because at line 6, we have one object in the pipeline. That one object is a map. It's called degree distribution, and we want to sort within the one object. So that's why we're doing a local scope.
Interesting. Okay. Interesting. Now, just for curiosity, if you had not capped degree distribution and you tried to do this, right, because you did not have that one object degree distribution in the pipeline that you were now ordering on, what would you be ordering on in that point if you did not have the cap? Would that even work?
Yeah, I mean, so my recommendation always, not for right now, because we won't be able to get onto more examples, but my recommendation always to anyone who has these questions is to fire up a notebook and see what happens. I will skip ahead and let you know what happens. So for this, if you don't add in cap, you're essentially going to get a stream of results of what completed first. And applying an order will order each individual entry instead of the full map, like getting a map in descending order.
Cool.
So if you want it to be a deterministic traversal, you want to make sure you force it to stop and get every object and then order the full map.
You know, I didn't say it out loud, but you saw me clap maybe for a second there. I was actually happy to hear that what you said was pretty darn close to what I had in my mind. I just didn't say it out loud, and I swear I'm not doing one of those things where I'm taking credit for it after the fact. Because I could just like you, but no, I was wondering if that's exactly what was going to happen there. That without the cap, right, then you have all these other streams that you're essentially now ordering on, instead of having the single finished object that you are ordering the objects within that map.
Exactly.
So yay, cool, very cool. Okay.
Perfect. We're
all on the same page. By the way, before we move on, Frank, our friend Frank, hello Frank. Had mentioned here, let's see, I had bags of fun getting the notebooks to go today, and I finally defeated the bulk loader. So
nice.
Awesome job, Frank. Yay, I'm glad to hear that you got into it a little bit.
Yeah, once you get that bulk loader up and running, for chapter 10, we load like 20 million edges in under 2 minutes. That thing is a beast. I love our bulk loader.
Bulk loader's awesome. And you can use it not just for Gremlin, but for Cassandra, for all the stuff. Yeah, it's a nice tool.
Awesome.
Yeah, so using copy from should move to bulk loader.
Yeah. Thanks for the questions. I appreciate it. I'm glad to see you again, Frank. So for this next set of queries, we're going to follow the exact same pattern that we already introduced. Okay. So we're going to start from a tower, and we're going to walk out one neighborhood.
Okay.
Following the same pattern. Pardon me, not path. We're going to follow the same pattern where we start from Georgetown. And then we're going to walk in through the edges and just project that first neighborhood. So you can already see, you can already see that we have so many more sensors that are directly connected to towers. So this concept of branching factor is hitting us right away.
Yeah, you can see that right off the bat.
Yeah, exactly. So. And David, this one's a little hard. Can you show me, or can you tell me which example we're at here? It's hard for me to see on the screen.
We are at find all sensors that connected to Georgetown first attempt.
Okay, right. So for this one, so we could walk through the exact same pattern that we did going from sensors up, but we kind of walked through that, right? We're just going to slowly be walking out one neighborhood. So what we want to do is we want to just wrap up that same until you've reached a certain sensor. We want to follow that same pattern of until repeat, right?
Yes.
So this time we're going to start from Georgetown, and we're going to keep walking in through these send edges until you reach a sensor. So we're going to keep walking all the way down until you reach a sensor. And then you're also going to be calling simple path again to ensure that we don't have any cycles. But for this one, whenever we do this is, again, a really, really, really long recursive query. And we have a really expansive branching factor. But I'm also trying to look at the result sets that you have here, and it's super hard for me to see. So sorry, David.
No worries. But I mean, you can see in this case that my results are, in fact, a set of sensors here, going from Georgetown.
Exactly. Okay, I got it. And so we lifted the exact same template from the last time, where our stopping condition was that it was to another sensor, correct?
Yes.
Except
yes.
Everything that talks to a tower is a sensor, right?
Well,
yeah, it is. So
I guess so. Yeah. Okay.
So the first query we just did before walked from the tower out to the first neighborhood. Okay. And then we were like, oh, let's be smart developers and computer scientists, and we're going to use our same until repeat pattern that we did in the last one.
Right.
But we've actually just walked out the first neighborhood, because until you reach a sensor is the first neighborhood.
Right. That's exactly, that's what's coming next. Okay.
Yeah. And so that's why this is the first attempt, because I also wanted to show you guys how I make mistakes, or how I kind of think through my reasoning, where I was picking other patterns of writing gremlin code and just lifting them to the new problem. And I realized, well, wait, if I start at Georgetown and I walk out, or I walk in my send edges until I reach a sensor, I'm not going to go any further than the first neighborhood.
That's right. And that's why we terminated with simple. I mean, every one of these is a single sensor, and that's it.
That's it. So that's why this was the first attempt, because again, in the spirit of showing you all how graph practitioners work with graph data, I just wanted to show you all my own road bumps as well. And this is one of my first road bumps.
Okay.
So now we kind of need to remove that guardrail. We need to remove it and say, I need to start at this tower and walk out for any non-cyclical path. And that's the next one. And you'll see in the text, and you'll see in this notebook, do not run this, because this actually traverses every single possible path in your entire graph, starting from the Georgetown Tower. And it's because you have no guardrail. You have no stopping condition anymore. It's just going to keep going through every branching factor from this tower to its sensor. And it's going to keep picking up, say, 10 more sensors at every level. And this was one of the harder problems that we had to solve when we were working with the power company, trying to figure out how to walk from the tower down to all possible sensors that connected to it. So we started here, and we realized, well, this is going to never finish because we're just processing the entire graph. So in the next section, I think we introduce depth limiting. Is that correct?
Reading what you have in here, you have it. I'm assuming so, because you say it's reduced scope.
Yeah, reducing scope.
Oh, I see. Find all sensors that connected Georgetown with 3 connections. So you're limiting the depth that you are going from that tower.
Exactly. Okay. So when you're walking through hierarchies in graph data, it's all about selecting intelligent guardrails on how much data you're gonna process.
Okay.
And so when we were walking from sensors up to towers, our guardrail was simple path. We had a significantly lower branching factor and a very deterministic terminal point, or we knew exactly where that query was going to end on a tower. And so it was much simpler to write it and to use the simple path as our guardrail. When we start from a tower and we're walking down to any sensor, the guardrails are a lot harder to figure out. So what we are doing in this version was showing you how to do depth limiting, starting from the root and going down with the repeat times pattern, which is essentially the way to hard code. Hard code is the wrong word, but it's the way to essentially say, I want you to walk out n number of neighborhoods. So we're going to start at a tower, and in this example, we're limiting by 3. We're doing repeat going in the send edge, non-cyclical paths, but only do it 3 times. So that means we're going to walk 3 neighborhoods away from a tower.
Okay.
And you can probably go ahead and run this query to get started. So we're going to do the same process of starting up at a tower, walk through 3 neighborhoods, and then we're going to look at the path that this took, starting from Georgetown, walking through to the 3rd neighborhood, and then inspecting its path. And we're following the same shaping of results that we did at the other time, or at the sensor query, where for the path object, we want to inspect every vertex on that path, and we want to look at either the tower name or the sensor name, using that if-then with the coalesce statement on, looks like lines of 8 and 9 there.
9, yeah. And that's what you see. So this one seems like this might be a fun one to actually visualize from the graph standpoint. If we were to remove the by modulator and coalesce and just go to the path.
Yeah, I haven't. You can try it. I actually don't know. I don't think that the path object in Studio lets you see the graph view. We'd have to do a little bit, more manipulation to that traversal to get it into the path view, but we can try it live if you want. I'm always up for trying things live.
Okay. Oh, that's right. Because you do. That's right. Okay.
Yeah. So I think if you just at times 3, when you're at times 3, you're going to have a set of vertices that are 3 away.
Okay.
Pardon me. So what you're essentially going to end up having is just going to be a set of isolated vertices in the graph view. If you're trying to look, that should give you a set of vertices for graph view, but they're all going to be, you can turn it on.
There you go.
So what you're looking at essentially is the 3rd neighborhood away from Georgetown. And you're looking at just the connections that exist at that 3rd neighborhood, but not the full path from Georgetown.
That's right. You don't see the full path. That's right. How might I do that? I mean, putting you on the spot, Denise, how might I go through, and at this point, if I wanted to actually see what that path from the Georgetown Tower was to the 3rd neighborhood away of all those sensors?
That's a really good question. And for graph visualizations in Studio, I have only looked at what Studio does is it pulls a set of vertices and then it gives you its immediate edges. So we'd have to collect every vertex along the way into one large set of vertices and visualize that. And so I'm trying to think how we would do that.
Totally putting you on the spot.
Yeah. We can play around with it and see. Because right now, at the end of times 3, what we have are the set of sensors that are reached, and it's almost like what we need is this is what I think we'd have to do. I think we would have to make use the aggregate step in Gremlin, which is going to make an object, and so after dev.vTower, we'd probably call aggregate like my group. And that's going to put the tower into my group. And then, you want to try it live?
Yeah, why not?
Yeah, let's try it. Yep. So aggregate my group, and then make sure we have a period at the end there. And then after in send, I think you want to do another aggregate so that we add all of those vertices at each neighborhood level into my group.
Now, so we actually want to aggregate again to my group.
Yeah, it's going to keep appending them into this big group.
I see what you're doing. Okay. Oh, we need my.
And so then we have times 3 at the end, correct?
Yes.
So let's try after that. Let's try cap my group, because that's gonna cause everything to come to finish into. And then we want to unfold it, and that would put every vertex into the stream. I'm not confident on this, by the way.
Well, we're gonna see what's gonna happen. Nothing like it. Who else wants to keep putting Denise on the spot? Just raise your hand.
Hey, that is the full graph.
Oh, look at that! Now, totally, that was not practiced. I just made Denise do that just right now.
So what we did. Great. So here's what I was reverse engineering in my brain. I know that Studio will display for you a vertex and all of its connected edges, and then endpoint vertices. So what we wanted a full list of every vertex we touch on the way.
Right.
And so once we start at the tower, we want to put that in a list. And then at every step on the neighborhood, we want to add those into our list, which we were calling my group. And we do that with the aggregate step. So we keep adding in these vertices on every single neighborhood. At the very end, we capped the entire group to make one object, and then we unfolded it into the stream so that we can render every vertex that we approached on the way, along with all of its edges.
Now, if we hadn't limited this,
great question. I'm kind of glad I was able to figure that out on the way.
You're like, woo! If we had not depth limited this, then this might not be a very good idea. Well, for one, if we didn't do that at all, this thing would have been run forever. But obviously, as you increase this number, right? Like if we just go stupid.
Yeah, you want to try 4?
Oh, I went for 10.
Well, I was
was that okay? Just go for it. Hey, this is only on my local Docker instance, right?
But there it is.
See. It actually rendered it out.
So it looks like you have the vertices colored according to their type. So the green vertex is the tower. The blue vertices are the sensors. See, now this is going to turn to be the most fun part, live Gremlin querying. That's cool. That's actually a really cool view into the graph. You should take a picture.
Oh, let's do it. Taking a picture right here.
Yeah, let's tweet up the live gremlin traversals that we were doing during today's session. So
here we go. We'll do that. And by the way, while we're doing this, so Frank again, our friend Frank, he mentioned before, he said, Chapter 10 crashed the database 4 times before I defeated it. Funny enough, I wonder, Frank, for the graph database that you're using, are you doing it through the Docker image? And if you are, what kind of memory settings do you have on that? I'd love to know more about it, actually, because I have a feeling if you're using some of the defaults, and when you're asking it to do that much, it may not be much. I think the default for Docker is like 2 or 4 gigs.
It is 2, and I have mine up to 8. Then I also, I'm curious, let's go look up, David, where they are on releasing DataStax Desktop, because DataStax Desktop has the container. Yeah, it has the container properly sized to run these out of the box. So
that's what I'm using right now, actually. And I will do that here in a moment. Frank did ask, how have you called up the display? So when you're in Studio, Frank, now you'll notice that the interface here is dynamic, and it will change depending on the data that you have coming out. So if I put this back down to 3, let's say I take off that unfold step, and I rerun this. And what's going to happen, notice I no longer have that option, right? Because I just have this JSON output out here. Mm-hmm. So when the data is in a format that Studio can support in different modes, it will automatically give you the buttons for those particular modes. So you'll notice this time, when we're using the unfold step here, once it finally finishes, I think it's going to default back to the fact that I had the graph option, the visual option chosen.
It's detecting the objects, and what it can render are actual vertex objects coming back from the database.
Okay, and while we're waiting for that, he says, yes, I am using Docker. So I would say it sounds like you got past it, crashing it, but I would say that you need to ensure that you have the right amount of resources in Docker. I mean, obviously for what we're doing with the Docker image and the stuff here, it's meant to be, just like a quick database that you can spin up and go and experiment and such. But if you start really increasing, the amount of resources it needs, you need to increase those. Yeah, I would say, honestly, I'm running mine at 11 or 12 gigs, just because I run a bunch of different things in Docker. But here, as you start to get into more intensive workloads, you're going to need a little more memory.
Yeah, and I'm wondering if something if something happened, because I don't know. There's no reason that query should still be running.
Yeah, exactly. That should have already completed. So here, let me do this real fast.
But yeah, I think that was a really great question, David, there at the end, to kind of show the power of graph visualization. But sometimes whenever you're kicking off these really long running hierarchical traversals, if you're processing too many variables, once they complete, making sure that your query is completed, it can start to really resource constrain your system, which looked like is what happened just there.
Yeah. I wonder. Yeah. Who knows what I did to my.
Who knows? Who knows?
Oh, there it is. Yeah, there it is. So notice in this difference this time though, now that we added the unfold step, because of the format that the objects are in, then I will automatically get an option. Where in this case, I can review the results as graph. Now you're seeing some other options here that the Studio does, where you can actually do some pretty charts. You can start plotting your data on like a bar chart or a line chart or something. But if you're specifically looking for the graph visualization, then it will automatically show up when you have the right object types.
Yep, absolutely. Great, great ending query there, David. I love the random question.
Yeah, no problem. I appreciate you going along with it, as I just totally put you on the spot.
That's fine.
and watching you figure that out, like I wasn't trying to zinger you.
No, that's great.
Like, I want to see this in the graph. Like I actually want to see the visual here.
Yeah, well, I had the opportunity to be taught by the best, and I honestly shout out to Daniel Cuppets because I remember I was sitting here thinking, I think I've approached him with similar queries years ago. And he taught me through how to think about aggregate and how to make groups. So in that moment, when you're asking me that question, I thought, well, what would Daniel Cuppets say? and so I appreciate that.
All right, with that, so I think that's it, Denise. We're at the end of this notebook. It's right at time. So we got through our notebook like boom, like right when we expected to. So I would think that maybe that means next week we're going to jump into chapter 7. Is that right?
Yeah, chapter 7. So in chapter 7, we're going to solve the problem that we just ended with the real way. We're going to show you how to remove the barriers for limiting by depth when you're walking from roots to leaves, because we're going to use something we haven't used yet, which is time. These sensors and messages are happening at a certain time. And so we're gonna actually use the time property that's stored on our edges to walk through valid communication trees and invalid communication trees.
Oh, interesting. Okay, well,
Yeah,
good. I look forward to that.
Yep.
Look forward to this. Is actually going to be communication trees within our sensor network as well.
Yes, yeah, we're going to still be within the sensor network, but now we're only going to be talking about valid communication. So you can kind of think of it like catching a subway train too early or too late. Like if you show up at the platform and the train's already left, you're not on the train. Or if you show up to the platform and you have to wait for 20 minutes, these messages and these sensors don't live that long. So they're not going to actually be able to continue on a successful path. So some of the implementation details of how this works is that you have to show up at the right time in order to be passed on through the network. And that's what we're going to look at next week. Actually, 2 weeks from now. 2 weeks from now.
Oh, is it 2 weeks? We're skipping next week, aren't we?
We are skipping next week, so we'll be back in 2 weeks.
Next week. That's right. We'll be back in 2 weeks, and we'll see everybody for another Graph Data and Code with Denise and David. Thank you again, Denise, and for humoring me when I put you on the spot there at the very end. Thank you all for watching, and I want to make sure that we end on time today, and we'll see you everybody in a couple of weeks. Awesome.
Thanks, everybody.
Bye.